In this video, I am going to talk about hyperparameters, and I'm going to continue talking about hyperparameters into the next video, but that's going to move more towards convolutional networks hyperparameters rather than just base neural networks hyperparameters. This first slide is going to start off with just some of the easy ones. The first one is batch size. Usually when we use neural networks, we are doing it because we've got quite a lot of data. So what we do to handle that data, because it's too big to process all of it at the same time, is let's say that this is our data set. What we'll do is we'll actually sample a mini batch. So we'll start off with just taking a few of these at random, and then we will do one forward pass and one backwards pass with just this mini batch. So you'll go forwards and then you'll go backwards, and remember the back propagation is when you calculate gradients, so that's when you update the weights. So you do that with just this mini batch, and then you do the next iteration with a new mini batch, which is of all 4 different samples or whatever size you use. So you'll choose 4 more samples, and then you'll do another forward pass followed by a backward pass, etc., etc. Once you've been through all of these samples in your whole data set or your whole training set, then that counts as one full epoch. So the idea here is that when you randomly sample these batches, they are a small representation of the entire data set. So the gradients that you calculate are going to be representative of where you need your gradients to go for the entire data set. So this helps you essentially learn the data sets with just a small proportion of it, just because the data set's going to be too big to do all at the same time. The number of epochs is going to then control how long you're going to take to actually train your data. So if you just do one epoch, then you'll have seen every single data point exactly once, and that might not be long enough. So usually we might do 50 to 100 epochs, but the more epochs you do, even though you generally expect better training performance, the more likely you start becoming to overfit. So in a future slide, I'm going to talk to you about overfitting and how we can automatically stop when we notice that we are at risk of overfitting. Lastly, the learning rate just controls how much the weights are going to shift for each iteration that you do. So every time you calculate gradients, you are going to multiply that gradient by this learning rate, and that essentially just stops a common problem where I'm not going to explain to you the full ideas behind stuff like stochastic gradient descent, but essentially you have, let's say you have a gradient that looks like this, and you essentially are trying to find the minimum point of this curve. The problem is if you start off here, then your gradient is going to push you across over there. And then the next time you're going to see, oh, actually the minimum point is in this direction. So you're now here, and it's going to push you all the way over there. And this keeps going on and on. You keep missing this optimal point. And that's a big problem that we often have. And the solution is you just divide the gradient that you have by something like 1,000. So now you're only going down this much. And what this means, if we switch to green, is that from this point, if we start again, but now we're using this learning rate, we'll instead go exactly down like this. And if we get the same problem where we go this way and then back this way and then back this way, that's not such a big problem anymore because we're already very close to the optimal point. So that's the learning rate. So these are a couple of the basic hyperparameters that you might want to look to tune. We're expecting that you do try a number of these things at different, try different versions of these, maybe a batch size of 16, maybe a batch size of 32. You can try loads of different things and work out what's worked best, and this will comprise this will be your iterative development mission. So when we talk about overfitting, one of the optimal ways that if we had completely unlimited memory, one of the best ways that we could deal with this is by training lots of different neural networks and finding the average of their results. So if you have, I'm just going to draw a neural network like this because we go from a high dimension to a low dimension. So just imagine that this sort of thing is exactly what we have here, but just a faster to draw version of it. So if we have lots of these, which are going from big representations of data to small representations of data, if we get hundreds and hundreds of these, then we could take the average of all of them, and then we'd be pretty good against overfitting. The problem is these neural networks are so computationally expensive. If we tried to train 200 of them, then it would just take forever. If you remember from the last lecture, we have these models that take 2,500 days to train. Imagine trying to train 100, 200 of them. It would just be impossible. So instead, we have this algorithm called Dropout, which has been proposed, which tries to do something which is very similar, but without the computational cost. The idea is very simple. Every time we take a mini batch and we go through the network, we are going to delete some proportion of these nodes. So that's going to look something like this. So notice here that we delete the nodes and we delete all of the edges as well going towards those nodes. So you've got to remember that this is only for one iteration. So we do the forward pass and then we do the backwards pass, and we do that on just these nodes, but then all of the nodes come back, all of the weights come back, and we randomly select another proportion P to eliminate. So this is just what we eliminated the first time around. Second time around, maybe we're going to get rid of this one, and this one. And we do this over and over and over again for essentially every time we do any kind of forwards or backwards pass through the network. And what we get is this almost kind of mirrors the idea that we're going to have hundreds of different networks and average them. In this case, we've got hundreds of very, very similar networks, but slightly different ones that we're learning throughout training. And what this does is quite often neural networks will become really, really dependent on, say, one of these nodes, like exactly one of these nodes. And now this isn't possible because if this node gets randomly deleted for a certain iteration because of dropouts, then the network is going to have to be able to learn how to get to a good classification performance without using this node. So this dropout, it's a regularization technique which stops the network relying on specific nodes, which can really help it to avoid overfitting. So the other thing is introducing this idea of a validation set. Again, I talked about this a little bit in the first lecture, but this is maybe a better representation of what I was trying to say. So you can split your training set into a training set and a validation set. And you remember, you still never seen the test set, so this is perfectly legal in AI terms. And you can do a practice test on this validation set. And as soon as you see that this validation set is starting to go up in performance, then you can see that your model, your trained model, is overfitting. So even though this training error is going down, because your validation error is going up, you know that you're overfitting. So you can code the network to automatically stop when it sees this trend that the training set's going down or staying even and the validation set is going up. This is a graph from one of the most famous papers in AI ever. It's the paper that introduced the idea of residual networks, or ResNets. And I want to ask you, if we've got a 20 layer network, so this has got 20 convolutional layers, and the training error is down here. Now, if we take the exact same network, but we just add more of the same layers that we've seen before, so that we've got 56 layers. Now the training error goes up to about 5%. So it's down from 1 or 2% to about 5%. Does that mean that this 56 layer network is overfitting? Have a think about this. I'm going to talk about this more when we come to talk about ResNets in lecture 6.